Okay, let's just jump right in. We're going to break down one of the most important chapters you'll face in Class 10 science. Yep, it's chemical reactions and equations. And I promise you, by the end of this, you're not just going to understand every single key concept, you're going to learn a super powerful method to absolutely nail those questions in your exams. So let's get started. I mean, just think about it for a second. How do you go from a pile of ingredients to a delicious cake? You start with things like flour, sugar, eggs, right? They're all totally separate things with their own look and feel. But once you add some heat and, a little bit of chemistry magic, they turn into something completely new, a cake. And that whole transformation, that process of making something new from different starting blocks, well, that's pretty much exactly what a chemical reaction is. All right, section 1, reactions all around us. So let's start with the basics right at the beginning. What is a chemical reaction, really? And maybe even more important, how can you actually see one happening out there in the real world? Getting this down is like the foundation for everything else we're going to talk about.
Okay, so here's the textbook definition for you. A chemical reaction is basically a process where some substances, let's call them our ingredients, they rearrange their atoms to make completely new stuff with totally different properties. The classic example, the one everyone learns, is hydrogen gas reacting with oxygen gas to make water. Think about that for a second. You start with two gases you can't even see, and you end up with a liquid. That's a huge change, a fundamental shift in what the substance is.
So to even talk about these reactions, we gotta know the lingo. It's super simple. The starting stuff, our hydrogen and oxygen, those are called the reactants. And the new thing that gets made, water in this case, is called the product. It's a really simple but super important difference. Reactants are always on the left side of that arrow, and the products are on the right. Easy.
So how can you tell if a reaction is actually happening right in front of you? Well, there are a few dead giveaways. We can remember them with the word facts. F is for formation of a precipitate. That's just a fancy way of saying a solid suddenly appears out of nowhere in a liquid. E is for evolution of a gas. Think bubbles. C is for a change in color. T is for a change in temperature. It might get hotter or colder. And S is for a change in state, like a solid turning into a liquid. Those are your 5 main clues to watch out for.
Okay, section 2, the language of chemistry. So now we know what our reaction is, but we need to learn how to, write it down. We do that with chemical equations. And there is one golden rule, one thing that is absolutely non-negotiable. The equation has to be balanced. And this isn't just about making things look tidy, okay? It's like the fundamental grammar of chemistry.
But why, though? Why do we have to bother with all this balancing stuff? I mean, it seems like a lot of extra work, doesn't it? Well, there's a really, really good reason. It's because every single chemical reaction in the universe has to follow one fundamental, absolutely unbreakable law. And this is it, the law of conservation of mass. It says mass can neither be created nor be destroyed. It's that simple. You can't just poof atoms into existence, and you can't make them just disappear. Whatever you start with, you have to end up with the same amount of stuff. It just gets rearranged. So what does that actually mean for us? It means the total mass of all your reactants has to be exactly equal to the total mass of all your products. That's the rule. And since mass really just comes from atoms, it means the number of atoms for each element has to be the same on both sides of the arrow. The number of iron atoms on the left got to equal the number of iron atoms on the right. Same for oxygen, same for hydrogen, same for everything. That's what being balanced really means.
All right, section 3, the art of balancing. Okay, now this is the part I know you've been waiting for. I am about to give you the secret sauce, a simple step-by-step method that will let you balance pretty much any chemical equation they can throw at you in an exam. Seriously, no more guessing, no more random hit and trial, just a clean, foolproof system that works every time.
Here it is. It's a simple 4-step process. Just follow this order every single time. Step 1, balance your metals first. Things like iron, aluminum, copper. Step 2, then you balance the nonmetals, but hold off on oxygen and hydrogen for now. So things like chlorine, sulfur, carbon. Step 3, next up, you balance the oxygen atoms. And finally, step 4, you balance the hydrogen atoms. Think of it like this: MnOH. Metal, nonmetal, oxygen, hydrogen.
Got it? Let's put it to the test.
Okay, let's try it out on this classic reaction. We've got iron reacting with steam, which is just H2O, to make iron oxide and hydrogen gas. Now, you can see right away this thing is totally unbalanced. We've got 1 iron on the left, but 3 on the right. 1 oxygen on the left, but 4 on the right. It's a mess. So let's use our MnOH rule and get this sorted.
All right, let's follow the steps. Step 1, metals. The metal here is iron, Fe. We have 3 irons on the right side, so we need 3 on the left. Easy, just put a 3 in front of the Fe. Boom, iron is balanced. Step 2, nonmetals. Well, there aren't any others besides oxygen and hydrogen, so we can skip this step. Moving on. Step 3, oxygen. We've got 4 oxygens on the right. So to get 4 on the left, we need to put a 4 in front of the H2O. Now our oxygen is balanced. Okay, last step. Step 4, hydrogen. By putting that 4 in front of H2O, we now have, 4 times 2. That's 8 hydrogens on the left. So we need 8 on the right, too. We just put a 4 in front of the H2 because 4 times 2 is 8. And look at that. It's perfectly balanced. 3 iron, 8 hydrogen, and 4 oxygen on both sides. No guessing, just following the rules.
Section 4, a tour of reaction types. Awesome. Now that you're practically a pro at balancing, let's do a quick run-through of the main types of reactions you're going to see. You can think of these as, different categories or common ways that chemicals like to interact with each other. So this gives us a great little snapshot of the big ones. First up, you've got combination reactions. That's pretty self-explanatory, right? 2 or more simple things combine to make one more complicated thing. Then you've got decomposition, which is literally the exact opposite. One big, complex thing decomposes or breaks down into simpler little pieces. And then there's displacement. This is where a more reactive element comes along and basically kicks a less reactive one out of its spot in a compound. It's kind of like a chemical substitution. Let's check out some real examples to make this crystal clear. For a combination, look at magnesium and oxygen. They are combining to make one single product, magnesium oxide. Simple. For decomposition, see how that one thing, lead nitrate, is breaking apart. It's decomposing into 3 different products. And for displacement, check this out. The zinc atom literally displaces the copper, booting it out of the copper sulfate. See how each name perfectly describes what's happening? Okay, one last super important idea here, energy. Some reactions release heat, making things around them feel hot. We call these exothermic. Think exo for exit, like heat is exiting. Respiration in our bodies is a great example. On the flip side, some reactions need to absorb heat from their surroundings to even happen. These are called endothermic. Think endo for enter, like heat is entering. They make things feel cold. Photosynthesis is the perfect example, because plants have to absorb all that energy from the sun to make it work.
Section 5, cracking the exam. All right, we've gone through the theory. You've learned the foolproof balancing method. Now it's time to put it all to the test. We're going to tackle a real question from a past exam paper. This is where the rubber meets the road, where we see how all this stuff actually gets used.
So here we go. This is a real CBSE question. They want you to balance this equation, aluminum plus water, and figure out the values for P, Q, R, and S. Now is your chance. I want you to pause right here, grab a piece of paper, and use that MnOH rule we just learned. See if you can solve it yourself before I give you the answer. Go on, give it a shot. Okay, you ready? Let's break it down with our rule. Step 1, metal. That's aluminum. We've got 2 aluminums on the right, so we need 2 on the left. So P equals 2. Done. Step 2, nonmetals. None here. Skip. Step 3, oxygen. We've got 3 oxygens on the right. To get 3 on the left, we've got to put a 3 in front of the H2O, so Q equals 3. Almost there. Step 4, hydrogen. That 3 we just added gives us 3 times 2, 6 hydrogens on the left. To get 6 on the right, we need a 3 in front of the H2, so S equals 3. And what about R? Well, when there's no number in front of a compound, it's just a 1, so R is 1. And there are your answers. P is 2, Q is 3, R is 1, and S is 3. See how that method just walks you right to the answer? No stress.
So, there you have it. We've totally unpacked the core of chemical reactions and equations. You now have the tools to read, to write, and to balance the language that chemistry is written in. But the most important thing now is to not just see it on a piece of paper, but to see it everywhere. So my question for you is this. Now that you speak the language of chemistry, what reactions are you going to notice in the world around you today? Maybe the rusting of a gate, the food you cook for dinner. The entire world is basically a giant chemistry lab, and now you can finally read the signs.